Hello everyone, I'm Sami Alabed from Department of Computer Science, University of Cambridge. I'm here to present our work on high-dimensional Bayesian optimization with multitask learning for RocksDB. Let me first introduce what is RocksDB. RocksDB, this is embedded key versatile key value store. It's used in multiple different places. For example, in Apache Flink uses it as a way to commit messages and provide reliable delivery of messages in distributed system. It provides this versatility by exposing large number of configurations that the user is expected to know how to tune. These parameters requires knowledge about what's the objective of the system is, what's the workload characteristic, and even understanding of how RocksDB works internally. So finding these optimal parameters could be cumbersome and requires many iterations and experiments to find the best values for your system. In the thesis of this work, we will look into how can we find these configurations as fast as possible to reduce the number of experiments we have to conduct. So first, let me start by introducing what is Bayesian optimization in a high level. In tuning a system, Bayesian optimization will most likely be one of the best tools to use for it. The way it works is it interacts with the real system by building first a model of the system, and it's basically mirrors its understanding of how the system should behave. And then it has something called an acquisition function. This optimizer tries to find the best parameters for them based on the model it understands of the system. So effectively, by building this model and then trying to optimize the model itself, you reduce the number of communication with the real system. And then when the acquisition function finished experimenting with various values, it just reports the best. It's the one that thinks it's the most optimal for the system, and then reports it back to the system where we run it and see and observe how well it does. So the Bayesian optimization loop is basically a framework where we can plug and play different parts of it. For example, the model is the one we are interested in here because can we find ways we can inject our expert knowledge into the model and reduce like the curse of dimensionality, which is a very popular problem in ML scene, where you increase number of dimensions, which is the number of parameters we have in RocksDB, and the number and what the model is learning every episode diminishes. So we looking into ways we can, like, even though we increase number of parameters, we can still learn from every experiment. So first, let me introduce in a high level why multitask sounded like a plausible, useful method to use. So first, a standard model usually builds an experiment result, and then you have the model, and the model tries to mimic the objective and the parameters, impact of parameters on the objective. In a multitask setting, now you have the parameters, but not a single objective, which could be the throughput of RocksDB, right? Instead we can we can ask it to model multiple objectives. Now these objectives, because we can choose what these objectives are, we can choose objectives that are related to the throughput. So if we are interested in increasing throughput, maybe we are also we should reduce the number of I/O stalls on the system, for example. So we can model each of these as a task based on our expert understanding of how the objective is and what influence the objective. And now, by providing this wider context, the model learns a lot more from every episode and experiment it sees. By introducing multitask, we increase the inference complexity. So we looked into ways of like choosing manually grouping parameters to reduce the dimensions, which again, the dimensions are the number of parameters we have or we're looking at. And because now we separated the training into multiple different tasks, we can group a set of parameters to a specific task. So rather than considering all the parameters impacting all the tasks, we say, okay, these 4 or 3 different parameters only impact the specific task. And this reduces the number of dimensions drastically. So that was the high level introduction, and let me go dive deeper into the method. So first of all, in Bayesian optimization, usually the most popular modeling method is the Gaussian process. Gaussian process is this machine learning model that is non-parametric and basically works by defining a mean function and the covariance of a kernel. So the kernel function is the one. The kernel is the one we are interested in, which basically learns the correlation between parameters and the observations. The Gaussian process proven to be very sample efficient. and able to converge very fast, but still suffers in high dimensional settings from curse of dimensionality, simply because higher number of parameters and you have very, very few number of samples. So here's where multitask optimization comes in. To enable to enable a Gaussian process to learn a multiple task, we can swap the kernel with something called an ICM kernel. This ICM kernel has two parts. It has the parameter covariance and has task similarity kernel. So the parameter covariance is basically a covariance of all the parameters you're learning against every single task you have. And then it also has a task similarity kernel, which basically learns how similar two tasks are. So now not only we are learning about a specific task, we are learning how these tasks interact as well and how similar they are. We were interested into increasing the I/O throughputs of RocksDB. Parsed all the stats dumped by RocksDB, and it was about 200 different statistics we could look at. From them we conducted 500 different random experiments, randomizing the values for these 10 parameters, and tried to look at the correlation between the stats dumps and against the I/O throughputs. From that, we narrowed it down to like two dozen of two dozen or two dozens of metrics we are interested in. Then we read basically the RocksDB documentations, and based on manual experiments, we narrowed it down to three very interesting tasks that by minimizing them, we also increases the throughput of RocksDB. So, for example, I'm not going to go in details here, but they are in the appendix of the paper. However, because have to copy every parameter, and RocksDB and Gaussian process already scales have an inference of n cubed, where n is basically the number of parameters multiplied by data samples. Now we multiply it by the number of tasks, it could hit scalability concerns. So we looked into decomposibility using clustering. As experts already know, certain parameters only impact subset of the system. For example, a level-based parameter will only impact the level matrices, which makes sense because these levels only come into effect when the system is doing a compaction between a level 0 to level 1. So we try to inject this knowledge using manual clustering, and in the future work, which could introduce unsupervised learning here. So what's the structure we derived for this paper? So we found the specific parameters that they were mostly influential to, for example, right amplifiers were these 5 different parameters. And based on this graph, we can see the maximum dimension is actually 5 rather than 10, because we no longer consider 10 different parameters. Now we only consider 5 for right amplifier at worst case scenario, and some of them only 2. For example, read block only has 2 parameters. So by reducing the number of dimensions, we also make it able to learn faster each task separately. And then we try to evaluate the system and see how well it behaves. So we are interested in two main key components, basically the conversion speed and it needs to find good parameters, right? So we wanted to find the best parameters as soon as possible. And this was based on our experiments against 10 parameters of RocksDB. They were all discrete values. They're all ordinal, so they have total ordering. They have various ranges, so some of them from 5 to 15, some of them in the millions, and so on. We used a simulation of Facebook's social graph, which is the one they reported in the paper, cited in our paper. And we used this as a simulation, and we run it for 15 minutes. And this simulation has a mixture of RocksDB operations. Some of them get, some of them put, some of them iterations. And we look at we compared against a couple of baselines. Some of them are standard Gaussian processes like GP and NI, and some of them are optimized Gaussian processes like GP blowtorch. We tried against random, some additive kernel methods. We tried against the tree structuring methods, GPE. And we can see like almost all the state-of-the-art methods provide a very, very similar I/O performance. So we report the median out of 5 different experiments over 100 steps. The higher the throughput, the better. On the x-axis is the throughput, and we have the minimum and the maximum and the median of the results. So almost all of them are very identical, but here where it comes I think the main contribution of the multitask and cluster multitask is the conversion speed. So if we look at most methods, well, first of all, in the bottom we see the defaults, and then in the blue you see the multitask, and in the green you see the cluster multitask. The first thing that strikes out is the cluster multitask. In the couple of first iteration, because they are random, they all perform very similarly, but then after a couple of iterations, it takes over and start learning. And we can see it converges very, very, very fast and finds results. Finds the performance 1.3 improvement over the default in just 12 steps, which takes the next best, next state of the art method, TPE, 72 steps just to find this slightly better slightly better configurations. The multitask, the blue in blue, and we can see it outperformed the cluster multitask, but it's slightly unreliable. Sometimes it does better, sometimes it does worse, and this is because with the cluster multitask we were a bit rigid by saying, okay, these parameters only influence these parameters, while the multitask one was like trying very, very experimental configurations. So this is a small trade-off between exploration and exploitation, I suppose. So in conclusion and summary, we looked into optimizing RocksDB using Bayesian optimization. We are interested into changing the into injecting expert knowledge inside the model of the Bayesian optimizer. We achieved faster conversion by simply injecting multitask expert knowledge, and we decomposed it as well. We decomposed the parameter, which led to more reliable and stable conversions. We see there's a lot of potential for using Gaussian mixture models or prostate clustering for choosing the grouping of these parameters. Hopefully you find this work interesting. Please read our paper, and if you have any question, I'm taking them now.